I guess we can start the second talk of afternoon session. Speaker is Dr. J.Duncan. It's Institute of Mathematics Academia Sinica in Taiwan. The title and abstract has been changed recently, but as far as I understand, the contents themselves are not too far away. Anyways, he's going to talk about rational triangles, elliptic curves, and sporadic groups.
Okay, thank you very much. I'm thrilled to be here. Thank you very much to the organizers for this opportunity, and thank you for coming to this talk, which will be an introduction to Moonshine. And I'm going to motivate it through a specific example. It'll be a kind of focused introduction. All right. So begin with triangles. So stepping back in history a little bit, 1,000 years or so. And there's an Arab manuscript with this, which poses this problem. For a given integer k, find another integer c such that c squared plus k and c squared minus k are both squares. Okay. So this has been called the problem of congruent numbers. And here is an example. 24. What do you think? Congruent or not congruent? Is there a c such that c squared plus 24 is a square and c squared minus 24 is also a square? Yes, exactly. Exactly. C equals 5 does the trick. All right. So if c squared plus k and c squared minus k are both squares, well, they have the same parity, so their square roots must have the same parity. So that means we can take the two averages and get integers both times. And having done that, what's the relationship between a, b, c, and k? Well, a squared plus b squared equals c squared, and k is 2 times AB, which is to say it's 4 times the area of the triangle, the right triangle, whose side lengths are A, B, and C. Okay. So you can say that 24 is congruent because it's 4 times the area of a right triangle with integer side lengths. All right. So the modern formulation say that D is a congruent number if there are rational numbers a, b, and c, such that D is the area of the right triangle with side lengths a, b, and hypotenuse c. Okay. So 6 is congruent. Well, this is the number we just gave. 6 times 4 is 24. 6 is congruent because 3 squared plus 4 squared was 5 squared. 24 is congruent. We've just seen it. And 157 is congruent because of this identity. So the problem of congruent numbers is still interesting because it's not that easy. So this example comes to us from Don Zagier. Yeah, so indeed it's an open problem to determine whether find an algorithm that tells you whether a given positive integer is congruent or not. Okay. All right, so let's turn this problem into another problem. We are, if we want to know if D is congruent or not, well, Well, here are two quadratic curves. We're interested in their intersection. Okay. So, okay. Well, and we're only interested in values of a, b, and c that are not 0. Okay. So fix c not equal to 0. All right, so now the first equation is equation of a circle. For a fixed c, it's a circle of radius c. And I guess we've all parameterized a circle before, but if you use like cosine theta, sine theta, that's a nice parameterization, but it's not very good at telling you which points are rational. So for which values of theta are sine theta and cosine theta rational? I don't know the answer to that question, but is C, suppose C is rational. If we draw a line from C with rational slope t, then this point here, whatever it is, its coordinates are rational. And then if we let t range through enough values, we'll pick up all the rational points this way. So that motivates, so now we do the algebra. So our lines are b equals c minus t times a. For fixed c and fixed t, thinking of b as a function of a. Okay, so that's the line through the point 0, c. Right, and we parameterize the rational points on this circle in this way. Okay, so we're going to do the high school algebra right now. So substitute c minus t a for b. We get this. Okay, so expand. All right, so now there's c squared on each side. We can take that away and get this. Magic. There's a factor of a. Now we can remove it because we're only interested in triangles with non-zero side lengths, right? So a is not 0, so we can remove a factor of a, and now we can solve for a. Okay. All right. A is a function of c and t, and then b is a function of c and t and a, so b is a function of c and t, and there's our parameterization. You plug in rational values of c and t, and you get all the rational points a, b, c on that quadric. A squared plus b squared, c squared. Okay. Now plug that into equation 1.6. All right. We get this. And yeah, I'm going to clear the denominators. And now the left-hand side is almost a square. Going to make it a square by multiplying by d cubed. Okay. So left-hand side is a square, and let's see. Okay, yeah, we can put the c squared over there. It's all the squareness is on the left-hand side now. So now we'll make a substitution. We'll take y to be the square root of the left-hand side and take x to be minus t times t. And we get this equation right here, which is cool because that's the equation of an elliptic curve. So this is a so-called d-th quadratic twist of this elliptic curve. And so what we've found is that if d is a congruent number, then there's some rational point on this curve, some rational numbers x, y that solve this equation that witnesses that. And moreover, this x and y are not 0. C and t are not 0. Okay, so we've come to curves. All right. So if there's a congruent number, if d is a congruent number, then there's a rational point on this curve with y not equal to 0. And this is if and only if you have a rational solution to that, if you have a rational point in that elliptic curve, then you can make a triangle that witnesses the congruentness of d, like so. Okay, now the rational points on an elliptic curve form a group, and that group is finitely generated thanks to more recent work of Mordell. And it's a fact that the rational points of finite order with respect to this group structure all have y equals 0. That's something you can check. So what have we found? We found that D is congruent if and only if this elliptic curve has infinitely many points, infinitely many rational points. Okay. So while we're on the topic of elliptic curves, here's another game you can play. You can ask, if you're given an elliptic curve, you can ask for its symmetries. So generically, you've just got plus or minus 1. So in that case, the endomorphism ring is going to be a copy of Z. But this example that appears in the congruent number problem, this kind of base elliptic curve, this elliptic curve at the base of the congruent number problem, it has a little bit more. So there's a order 4 automorphism right there. Because as a consequence of this, you get a copy of Z2. Well, Z adjoint I, but as an abelian group, you've got a copy of Z2, and in fact, that's all you get. It's a fun fact that if you work not over Q but over the field of 3 elements, then you get a little bit more symmetry. Or you still have this order 4 automorphism. So what does I mean if we're working over F3? Yeah, so x squared plus 1 is irreducible over F3. So F3 adjoin x mod x squared plus 1, that's F9. So F3 adjoin, F9 is F3 adjoin I. Upside down. Okay. But if we're working over F3, then we can also do this move, and that's an order 3 automorphism. Okay, so the endomorphism ring turns out to be an order in a quaternion algebra. Okay. So this is this special case where we get endomorphism ring of rank 4 that's call such elliptic curve supersingular. Third topic of the title, groups. Okay. So now just 180 odd years ago. So Mathieu introduced a couple of groups back in 1861, permutation groups of degrees 12 and 24. Here's extract from his paper. So if you're familiar with finite simple groups, so these are the groups M12 and M24, and this is exactly as much as he says about M24 in this paper. He doesn't really say a lot, and it was controversial for a while whether or not there was even such a group. It turns out there is. So the paragraph before, he's just essentially describing PSL211 as a subgroup of M12. Okay, so these are the finite simple groups M12 and M24. And well, one way to understand, so it turns out that if you have a 5-transitive group of permutations of some set, which is not AN or SN, then it's M12 or it's M24. So do you know what I mean by 5-transitive? So 5-transitive means any ordered 5-tuple can be mapped to any other ordered 5-tuple by some element in the group. So to make this all a little bit more concrete, I'm going to do a magic trick. All right. So have you ever anybody played cards before? I think so probably everybody's played cards. So if you play cards, then usually at some point you have to shuffle the cards. So the classic, maybe the most, I mean, I can't do it, and I don't know what portion of the population can, but like the riffle shuffle is the classic shuffle. Right? So you have a deck of cards, and you cut it in half, and then you like have it on the ground like this, and then they perfectly interlace like that. Okay, riffle shuffle. That's the riffle shuffle. So now do that on the board. So imagine you have 2 N cards. So I guess N is usually 26, something, but it could be anything you want. And label them. So they're stacked up. Uh-oh. Uh-oh. Okay. So they're stacked like so. And we'll number them 1, 2, N minus 1, N. So, and then there's the middle of the deck. Then N plus 1, N plus 2. But these ones below, I'm not going to call them, I'm going to give them different names. This is going to be N prime. N minus 1 prime. 2 prime. 1 prime. Okay, so these are our 2 N cards. Okay, so what does the riffle shuffle do? Well, there's actually 2 riffle shuffles. There's riffle, so-called riffle out, because you can choose which side has the card on the top, right? Like the card on top after you've shuffled could be number 1 or it could be number N prime. So riffle out is when you have the top card stays on the top. Okay, so after riffle out, then the order is 1, N prime, 2, N minus 1 prime. And then N minus 1, 2 prime, N 1 prime. Okay. Riffle in is the other one. Riffle in is when N prime is on top or when N is on the bottom. N prime, 1, N minus 1 prime, 2, 2 prime, N minus 1, 1 prime. Okay, so this is riffle in and this is and riffle out. So you may notice that there's something a little bit special about these 2 permutations. So, namely, right. So the outer cards are both labeled 1 with or without a prime. The next layer in is both labeled N. The next layer in is both labeled 2. There's a kind of central symmetry, just like there was here. There's a symmetry across the center of the deck. And similarly here, now 1 and 1 prime are together, n and n prime together. Okay. So here's the magic. You can do a magic trick. If you can do a perfect riffle shuffle, then you can do a magic trick because you know that the central symmetry is preserved no matter how many times you shuffle. Also, cutting the deck is another centrally symmetric. You just cut the deck, cut the deck in half, put the top on the bottom, put the bottom on the top. That's another centrally symmetric one. So then, like, you look at the card on top and you know what the card on the bottom is, even though the audience doesn't. Yeah. Okay. So and here's another piece of magic. So define, I don't know, Rn to be the group generated by riffle out and riffle in on 2 n cards. Then fact R12 is a big extension of M12, which is to say that if you make R bar the kind of induced action, the induced action on pairs, on these centrally symmetric pairs, then R bar, like if you just forget about if you just act on the n pairs instead of the 2 n individual cards, R bar 12 is exactly M12. Yeah. So now everybody knows one sporadic simple group. Okay. So there are 5 of the. So there are 5 groups known as mature groups. Because what happens is if you take M12 and fix a point, then the group you get turns out to be simple again. If you take M24 and fix a point, the subgroup, the point stabilizer turns out to be simple again. And similarly with M23. Okay, and these finite simple groups are called sporadic because they don't belong to any of the non-infinite families. All right. So what is this? So how does this classification story go? Well, the question of classifying finite simple groups goes back to 1892. And, well, it took a lot of work, but after about 100 years, the classification was achieved. So the finite simple groups are exactly the things you expect that they will be. It's apart from cyclic groups of prime order, the alternating groups for n sufficiently large, and the finite groups of Lie type. So what you expect, basically, is that if you have a finite simple group, then it's a Lie group, you just wrote it down over a finite field. Okay. And these sporadic simple groups are the exception to that expectation. Okay. So at this point, a talk in Moonshine focuses on the largest of the sporadic simple groups. So this is the monster. There is its order. There is its order written again. Okay, so it turns out to be, this group is very large. But, you know, there's infinitely many finite simple groups. In particular, there's a lot that are larger than the monster. Even A44 is larger than the monster. But the difference is A44, we have a good model for working with A44. So, you know, for a group that large, we can model it with matrices that are relatively small. To fit the monster into GLN for some n, that n needs to be at least 196,883. Even better, A44 is permutations of 44 points. The smallest permutation representation of the monster is ridiculously large. So somehow, yeah. Somehow the point is that the monster is small, not that it's large. Okay. All right, but really in this talk, well, for the particular story that I want to share today, it's the smallest of the sporadic simple groups is more important. Okay, so this is the group M11, or in other words, it's the group you get by doing riffle shuffles, combinations of riffle shuffles in and out, in and out, in and out, that keep the top card on the top and the bottom card on the bottom. It's one definition. So this is a sporadic simple group. Here is its order. It's a much more manageable number. And it's a 4-transitive subgroup of A11. Okay, so it acts transitively on 11 points. It's one of the small miracles of this sporadic group story that, well, this group M11 in particular, that it also has a transitive action on 12 points. So this is like two different, it's almost like there's two different groups, right? Or at least two different models. Like really different models for the same group. Okay. So this is kind of reminiscent of Galois' result that PSL2 over a field with P elements, well, it acts on P plus 1 points because it acts on the projective line over FP, which has P plus 1 points. But for certain P, it has a smaller non-trivial permutation action. So exactly for these values, 2, 3, 5, 7, and 11. Okay, so a question to keep everybody involved. So any guesses what the point stabilizer is for this 3-transitive action of M11 on 12 points? So M11 acts on 12 points. If I fix one point in choose a point, the stabilizer of that point should some group that acts transitively on 11 points. So what nice permutation groups do you know on 11 points? Okay, here is a hint. As an actual transitive action 11 points, okay, had that hint already. It has order 7,920 divided by 12 is 660. Okay, 660 can be written like so. I think maybe by now somebody can guess the group, right? It's got to be PSL2 of it. Yeah. Okay. Yeah, so these two miracles are connected. Galois theorem and M11 acting on 12 points. They're connected. All right. And try and tie these topics together now. Okay. We've made it to the 1920s. So Ramanujan, very shortly before passing away, writes this letter to Hardy and introduces so-called Mach theta functions. But as per his style, he doesn't define them. He just gives examples. Okay, so here's one example. So it's some Q series, and you should think of Q as e to the 2 pi I tau for tau in the upper half plane. The complex upper half plane. Okay. But Ramanujan like Q series, so here's some Q series. Here's another example from the last letter to Hardy. So these are so I think he gave 17 in total here in that letter. Here's two of them. Okay. So and here's a different Q series that was definitely known to Ramanujan, but I'm writing it down here because it's very, very similar to 4.1. But very different too. So the series G of Q is what Ramanujan would call an ordinary theta function, and what we would call a modular form, almost. So it's the partition generating function. It's essentially 1 over the J.Duncan eta function. Its coefficient, the coefficient of Q to the n in this thing is a number of partitions of n. All right, and it's a modular form because if we adjust it ever so slightly, then we have this transformation. Well, we have invariance under a suitable action of SL2Z. Okay. So thanks to work of Zweig's decades and decades later, we can make a counterpart statement for Mach theta functions now. Okay, so here's how it goes. So we make a similar adjustment, multiply f by a suitable power of q, and we add a correction term. This thing I've called S star. And so we get a function f hat now, and that satisfies invariance for a suitable action of SL2Z. Okay. Well, actually, it's only invariant for an action of a certain subgroup. It's like gamma 4 or something. But anyhow, a nice big finite index subgroup of SL2Z, nice congruent subgroup of SL2Z. Here's the correction term. Okay. So it's some integral of S of t, where S of t is something we would call an ordinary theta function. Or S of t is an honest modular, a modular form of weight 3/2. Okay. So the jargon is that f hat's called the completion of f, and S is called the shadow of f. S is some actual modular form that encodes the failure of big F to be modular. We call big F a Mach modular form of weight 1/2. Okay, so that's how Mach modular forms work. So I'm gonna maybe try and motivate this notion a little bit more. So for this, I'm going to pull out a specific family of subgroups of SL2Z, gamma naught n. So these are just this is just the subgroup of matrices that are upper triangular mod n. Okay, so given such a group, let G be a cusp form of weight 2. So concretely, that means that G is invariant for this action of gamma naught n and satisfies some growth condition as the parameter tau runs off to infinity. Okay, so with these conditions, we get in particular we get a gamma naught invariant 1 form on H. G of ZdZ. Okay, so if I have a 1 form, I can integrate it and get a function. It's gamma naught n invariant, so we should get a gamma naught invariant, gamma naught n invariant, so we should get a gamma naught n invariant function on H. Okay, let's do the calculation. So from, I guess, primary school math to high school math. Okay, so here's the integral. Let's test it for invariance under the action of gamma naught n. Okay, change the substitute gamma z for z. This is gammas and gamma naught n, and that this 1 form is supposed to be invariant, so that's what we get. Okay, and now we can simplify that contour. All right. Okay, so we failed because f is not gamma naught invariant, gamma naught n invariant, because that thing on the right is generally not 0. Okay. On the other hand, we have a function now that, okay, it fails to be gamma naught n invariant, but it kind of fails in a nice way. When you act with gamma naught n, you get your function back plus some constant depending only on the transformation, only on the symmetry you're acting with, and only on the isometry you're acting with, and not on the not on tau, not on where you are on the upper half plane. Okay, so classically such things are called abelian integrals. And this fits into the into the theory of Mach modular forms. This is an example of a Mach modular form of weight 0. G's got to be gamma. G was gamma naught n invariant. G was a cusp form of weight 2. So this is a Mach modular form of weight 0. So the moral of the story is if you play this out in different weights, then you get, if you play it out in weight 1/2, then you get the Mach modular, you get the Mach theta functions that Ramanujan wrote down. Okay. And I mean, so this integral over G is very unlikely to give you a rational number. Very unlikely to be rational. So the function f constructed in this way, these abelian integrals, as Q series, they have very transcendental coefficients. So, and in fact, that's typical of the theory. Mach modular forms have transcendental coefficients. randomly chosen Mach modular form has transcendental coefficients. Which is kind of interesting when you think back to Ramanujan's letter, because there's no way Ramanujan was writing down Q series of transcendental coefficients. He for sure was interested in integers. So how did he find his examples? Where are these? Somehow Ramanujan's examples are special. Where are they coming from? Okay, so here is theta function of so these theta. I'm introducing some theta functions, theta mr. These are the theta functions you get from the even lattices of rank 1. So the even lattices of rank 1 are the integer scalings of A1 lattice. And M tells you the scaling, and R tells you which coset. So AM scaled, A1 scaled by M has 2M cosets. All right, so these are the theta functions you get. Okay, now I'm going to use the language of Jacobi forms, Mach Jacobi forms. So Jacobi forms are a lot like modular forms. Well, it's going to be completely concrete. So here is the. So what does it mean to be a Mach Jacobi form of weight k and index m? It means that you satisfy you kind of can be written like so for some holomorphic functions HR, and then you have satisfy a transformation formula like this. Okay, that's what it means to be k weight k and index m. And there's some growth condition on the coefficient functions HR, so-called theta coefficients. So, HRs are called theta coefficients. Uh-oh. All right. Now, I'm also going to, so Mach Jacobi forms satisfy this growth condition. It's convenient to have a weaker growth, to consider functions satisfying a weaker growth condition, i.e. to allow some growth as tau goes to infinity. So these are so-called weak Mach Jacobi forms. Right. And we're going to specialize to weight 1. All right. And it turns out that when you specialize to weight 1 and you ask for Mach Jacobi forms with no growth as satisfying the stronger growth condition, there's just nothing. For any index, there is nothing. Okay, so that's why we introduce weak. So within that space of weak Jacobi forms, Mach Jacobi forms of weight 1 and index m, let's look at those that have the minimal possible growth. In other words, those that are as close as possible to being actual Mach Jacobi forms, as close as possible. So before there was an R squared up here, I'm going to restrict the growth to be q to the minus, big O of q to the minus 1 over 4m. Okay. So denote this space J opt, 1 comma m. And here's the question which motivates the talk. So this is the point of the talk is to answer this question. Are there any, what are, and in particular, are there any Mach Jacobi forms of weight 1 and index, optimal Mach Jacobi forms of weight 1 and index m with integer coefficients? Or with rational Fourier coefficients? Or even algebraic? Okay, we're going to answer this question. So to do so, I want to kind of have a little bit more control over the space. The space has some symmetry. This group OM Well, it's the orthogonal group of the discriminant. It's the symmetries of the discriminant group of the even lattice A1 rescaled by M. So kind of symmetries of this thing, or this thing, is OM. So that's the motivation for OM. And this group, well, by construction, because we used these theta series to define Jacobi forms, it acts in a very natural way just by permuting the theta coefficients around. Okay, so it acts on the space of Jacobi forms, so you can cut your space up into, according to characters of this group. All right. Now, there's another way to think of this group OM. You can also think of it as the group of exact divisors of M. Okay. So for every element of OM, there's a unique divisor of M satisfying these properties, and it turns out to be an exact divisor, meaning that it's co-primed. So N is exact divisors of M are the divisors of M such that N and M over N are co-prime. And this is a group with operation take the product and divide out the GCD once for each factor. Okay. So XM is a group and OM is a group, and they're naturally isomorphic actually. And the reason to do this translation is that these exact divisors of M, these label, according to tradition, these label the symmetries of the group gamma naught M. So to put it another way, the cosets of gamma naught M and its normalizer. All right. Okay. So the point is that given a character of OM, I get, in a natural way, a group that normalizes and contains gamma naught M. Uh-oh. Okay. And here's another tradition to use as simple a possible notation to denote these groups. So M plus N, M prime, N double prime, is a shorthand for gamma naught M adjoin these cosets Wn, Wn prime, blah, 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 where you remember Wn is defined like so. Just some coset of gamma naught M. All right, so if I have a subgroup of if I have a group of isometries of the upper half plane, then I can consider its orbit space. That's naturally a Riemann surface once I compactify it, and a Riemann surface without boundary, and it has a genus. Let's say it's genus 0 if the genus is 0. Okay. So for example, gamma naught M is genus 0 for exactly these values of M. What does 2n plus n mean? 2n plus n means gamma naught 2n together with the coset that's indexed by n. So gamma naught 6 plus 3, gamma naught 6 union W3 is genus 0. Gamma naught 10 union W5 is genus 0, blah, blah, blah. Okay. And everybody's memorizing the primes that are appearing here, right? Okay. All right, now to answer this question. So this is a joint result with Miranda Cheng from a few years ago. So it turns out that if you're, so basically, if you choose the character such that this group is genus 0, then this corresponding space of Mach Jacobi forms has a unique, up to scale, element with integer Fourier coefficients. So that's if you choose the character so that the corresponding group of isometries of the upper half plane is genus 0. If it doesn't have genus 0, then every Mach Jacobi form in this space has transcendental coefficients. Okay. Okay, so that's the answer to the question. All right, here are some examples. So right, and because I have an essentially unique example, so I can label them by it's natural to label them by these genus 0 groups, which are naturally indexing them. So this is the example. So it's labeled with a 2. So this example exists. I mean, according to this theorem, this example exists because gamma naught 2 has genus 0. So upper half plane modulo the part of SL2Z, which is upper triangular modulo 2, and then, throw in cusps, that turns out to be a copy of P1. That turns out to be a sphere. So because of that fact, we have this example, and here are its coefficients. So, okay, so I'm not telling you exactly what I'm just giving you like part of the Fourier series. I'm not actually telling you exactly what it is. Here's another example which exists because gamma naught 3 has genus 0. Okay. And actually, these two examples didn't come to it. So Ramanujan didn't write down either of these two. But he did write down the one which exists because gamma naught 6 plus 2 is genus 0. So now I'm giving you a very, just completely concretely, the optimal Mach Jacobi form of weight 1 and index 6 attached to the genus 0 group gamma naught 6 plus 2, and it's given explicitly in terms of F and omega from Ramanujan's letter in 1920. Okay. Now, these functions, phi, blah, 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 so you remember this optimal condition was asking them to have as little growth as possible as tau gets infinite. Well, the modular elliptic J invariant is a similar beast, right? It's a SL2Z invariant function on the upper half plane with the smallest possible growth as tau goes to infinity. Okay. All right, and right, well, just to recall the definition of this thing. So elliptic curve has a J invariant attached to it, and J of tau means J of the complex elliptic curve given in the usual way as a torus. Okay. So here's a classification of the Mach theta functions with integer Fourier coefficients that we get. I've just listed these genus zero groups, all the genus zero groups that we get. Okay. Let's talk about moonshine. So at least in the last 4 minutes, we should have some moonshine. Okay. So so this is the pretty famous story. So in 1970, kind of original story of inception of moonshine. So in 1974, Andrew Ogg proved that there's certain primes for which supersingular elliptic curves and characteristic, the certain primes P such that supersingular elliptic curves and characteristic P have a funny property. Their J invariant belongs to FP. All their J invariants belong to FP for exactly these these values of P. Okay, or to put it slightly more geometric, just to say it a different way, the supersingular points of x0, 1, the points that represent supersingular elliptic curves, they're defined over FP, nothing. You don't need anything more than FP for exactly these primes. Okay. And of course, you've seen exactly this list of primes already. This is the list of primes that appear as divisors of the order of the monster group. Okay. And well, a little bit later, John Mackay noticed that this number and this number are pretty close together. Okay. And actually, this number is not that far away from that number. In fact, this plus this. So this is weirdly similar numbers. Okay. But I want to tell a different story. So after Ogg's kind of moonshine, after Ogg's observation from 1974 that, well, Ogg's result from 1974 that kind of started off moonshine. So a little bit later, he looked at the supersingular points of higher level curves, higher level modular curves. So in particular for x02, he computed that the relevant primes, the special primes, are 3, 5, 7, 11, and 23. So you may recall that these are the prime divisors of the order of the group M24. Okay, so for the genus zero curve x02, we have this Mach theta function attached, this Mach Jacobi form attached to it with integer Fourier coefficients. Do you see? And here's part of the character. Here's an extract from the character table of M24. Do you see the moonshine? He sees it, right? So this 90 here is 45 plus 45. And these numbers have similar interpretations. All right, so how about supersingular points of x03? Well, we just get the primes 2, 5, and 11 now, but these are the prime divisors of M12. Here is the function that, well, here's one of the theta coefficients of the Mach Jacobi form that's attached to gamma naught 3. And now 32, you can see is 16 plus 16, 110 is 55. Actually, it's this 55 plus this 55. This is the character table of M12. It turns out M12 admits a non-trivial, admits an interesting double cover. And then the other component is related to the representation theory of this double cover. So 20 is 10 plus 10, and 88 is 40 plus 40. Okay. All right. So so the magic here is, so what you want to do, right, is to make this coincidence like more than just a coincidence, you want to replace 16 plus, you want to know what happens up here when you want to move across the character table. Right? So we want to be able to replace 16 plus 16 with 4 plus 4, and 110 with minus 5 plus minus 5, and still be getting good functions. And in fact, well, so this next piece of magic is it's almost forced, right? Because we've classified all the mock theta functions with integer coefficients. If we move along the character table, we're definitely still getting integers, or at least we're getting algebraic integers. Maybe we're not getting anything transcendental. So we can only land on those examples we've already classified, and well, that's how it goes. So right. So look at so these are somehow the examples that tell you the yeah. So these mock theta functions are telling you how to move across the character table in the case of x02, and similarly here for x03. Okay, and so in particular, Ramanujan's special examples also appear in this M12 example. Okay. All right. So in minus almost 3 minutes remaining, I'll finish the story. Okay. So weight 1 was a lot of fun. What's happening in other weights? Well, the next weight is 2. So and to keep the discussion short, we'll restrict to index 1. So weight 2, index 1. What's going on now? It turns out that we don't have to allow growth there, because there is an honest to goodness mock Jacobi form of weight 2 and index 1, and it's the generating function of the Hurwitz class numbers. The Hurwitz class numbers are the usual class numbers of imaginary quadratic number fields, but you counted them correctly because you weight them by their symmetries. So here's a concrete definition. So which I will skip just to kind of show you them concretely. So the class group of Q adjoin root minus 3 is 1, but there's more symmetry, right? The integers have 6-fold symmetry, so we divide by 3. The class number of the order of the class group of Q adjoin of the ring of integers in Q adjoin Q adjoin I is 1. We divide by 2 because there's extra symmetry. Okay. Q adjoin minus 7, class number 1, minus 8, class number 1. Q adjoin root minus 11, class number 1, so on and so forth. Okay, so this is and then, right, class number 2, minus 15. Right, so these are the Hurwitz class numbers. They define a mock Jacobi theta function, mock Jacobi form. Now, here is the mock theta function, the mock Jacobi. Here is the mock Jacobi form attached to gamma naught 3 and M12, and I'm gonna, so this mu and this theta and this eta are all completely concretely defined things. So what I'm doing here is defining a new mock Jacobi form phi 1. Okay, so there's the concrete definition of all those other pieces. Okay, when you make this definition, you get exactly this Herbert's class number generating function we just introduced. Well, concretely, you get 24 times that thing. All right, and the magic is that we have this. This is the graded dimension. This is generating function dimensions of some M12 modules. So we can move along the character table. We can replace 1A with arbitrary element of 2.m12, and it turns out that this definition you can still make sense of this definition and thereby get a 2.m12 interpretation of on this guy right here, which is to say there is which is to say Herbert's class numbers are naturally dimensions of representations of 2.m12, or rather Herbert's class numbers times 24. Okay. So here are the dimensions of the actual 2.m12 modules that we get. Okay. Now, because of this, we can do the following. We can prove the following theorem. All right. So suppose D is a square-free positive integer that's congruent to 3 mod 24. Then, there is a corresponding homogeneous subspace of this Herbert's class number module W, and you can ask if a particular representation of M11 appears there or not, and if it does, then D is not congruent. Okay. Thank you.